will be telling us about interaction and distributed private learning.
Okay. I did not get the last part of the joke, but yeah. So this is a joint work with Adam Smith, my PhD advisor, and Jalaj Upadhyay, who is supposed to be sitting somewhere here. The title of the talk is Interaction Necessary for Distributed Private Learning? I can really give this talk in 2 seconds, which is done. This is 9 a.m.
Yeah, glad we showed up at 9 a.m. for this.
So I have an obligation to spend more time on this. So let's do that. So so in this talk, what I'm going to show you is that if you have a distributed learning problem, then we'll try to look at protocols which are completely parallel and what can they achieve, and we'll also show some impossibility results which basically show that certain problems you cannot solve with completely parallel protocols. What is the setup? You have a bunch of devices. Each device has their data sample, and there's a server with the devices that are communicating to, and that's producing a model. This is the general setup of distributed learning. We'll put privacy on top of it, and I will just say in a bit what I mean by privacy here. The structure of today's talk. The first part, I will tell you about the guarantees, basically both the upper and the lower bounds, which will kind of give you some motivation to listen. My second part of the talk, the algorithms. If you're not motivated, you can leave the talk after the first part. And the third part basically says some of the impossibility results. So the result which I will be presenting is from 2017. There has been some work after that, which I will kind of allude to, but I will not get into the details of those results. Some of our lower bounds have been kind of superseded by newer lower bounds, which I will mention in a bit. Okay, so distributed machine learning. In a traditional machine learning setup, you have a data set and you train a model out of a classifier. In a distributed setup, what you have a bunch of devices. Those are in completely different geographical locations, and they're connecting to a server and producing a model. This raises both algorithmic and engineering challenges. From an algorithmic standpoint, you understand that you have to kind of ping the device, get that result, and there is some level of interaction. From an engineering standpoint, each of this communication is roughly in milliseconds. So if you try to kind of have this kind of setup, I've been told that each of this kind of pinging the device and getting information back is roughly in milliseconds. Moreover, when you are pinging a device to get some information, you are not even sure if the device is online to give you that information. So interaction causes both algorithmic and design challenges for distributed learning. So we'll see where things go from here. In the context of privacy, this slide is mostly boilerplate, but still I will kind of emphasize on this just because this is the first talk of the session, and also just to kind of emphasize what exact privacy model I'm working with. You have a bunch of devices. The devices are connected to the server, they're producing some result. In a typical differential privacy setup, you will have, like, if the adversary looks at the model, should not be able to figure out what the exact data sample was or get any information about the data sample in the data set. Here, along with that, we would assume that an adversary can actually look at the channel or actually sit at the server. In particular, it can look at the communication from the device to the server and still should not be able to decide which data sample the device had. This is essentially directing us to local differential privacy. So, in this talk, I will be focusing on local differential privacy. So the notion of differential privacy will be local differential privacy. In particular, in this definition, the complete transcript of communication with the device will be epsilon local differentially private. And as pointed out by Aaron, this is slightly different from what John was mentioning in his talk. So here I have the complete transcript to be epsilon differentially private. So that if you do learning from sensitive data, people have spent a lot of time on balancing the utility privacy trade-offs. In this talk, I'll try to motivate. There is another aspect you have to kind of balance the trade-off with, probably as important as the other two, if you want to deploy them in practice, that is the interaction with the devices, if you're dealing with a distributed learning problem. So, if you forget the rest of the talk, remembering this picture is probably useful. That along with utility and privacy, you have to actually balance the degree of interaction with the devices if you want to deploy any of the learning algorithms with privacy in practice. And this is not a story I just built up for this talk. So the motivation of the whole direction of research came from my time at Apple. After we deployed the private heavy hitters algorithm for Apple, the next thing was to do distributed private machine learning with local differential privacy. So it was a task given to me, and they said, like, there are papers, why don't you implement those? I started thinking about it, and my answer to them was that, in all honesty, I cannot direct you to do that work. And we actually did not ship that. Like, we did not even pursue doing the engineering, because I realized that our understanding of that whole space was limited, and that basically kind of gave this direction of research. So this comes from, like, purely from engineering standpoint. Okay. So what is this talk about? We'll show some new protocols that are almost completely parallel, which gets optimal accuracy under the local privacy model, and some impossibility results showing that you need some degree of interaction with the devices to get the optimal error. I'll get into a bit more detail in a few slides. So, what is an ideal scenario if I'm a designer, algorithm designer? Well, each device interacts with the server independently and only once. So how? The device decides a bunch of questions. The server decides a bunch of questions, sends to the devices. The devices respond back to the server with the responses, and done. This is amazing because you communicate to the device only once, and you do it completely parallelly. Question?
But do you allow adaptivity or not?
No, I'm saying, like, this is an ideal scenario. I would want an algorithm which is completely non-adaptive, completely parallel. Right? Okay. So I would want that for obvious reasons. However, the state of the art, at least before this paper, was by Duchy, Jordan, Wainwright, where they did have this property that you communicate with the device only once, but the algorithm was completely adaptive in the sense you talk to each of the devices in sequence, and you receive the message from the previous device to decide on the question you'll ask to the next device. How does it work? You ask the question, get an answer, ask the question, get an answer, and continue doing this. And you produce the model. So the number of rounds of interaction is equal to the number of devices. And remember, I told you this 5 millisecond, or like the communication in milliseconds. Now, if you try to train any method, any reasonable learning method with this under privacy, it almost becomes infeasible. Right? So, again, this work is about distributed private learning with local differential privacy. Yes. Yeah.
You described a particular way of going about it, but what in their derivation makes that an impossibility proof?
Oh, so we haven't gone to the impossibility. I will show that this is actually necessary for certain class of problems.
It's necessary to query in sequence.
Query in sequence.
Why?
No, that is the later part of the proof, but I'll say that, yeah, this is necessary. Okay. So first I will show algorithm that will use little or no adaptive interaction. In particular, if you have learning problems or ERM problems which are one-dimensional or constant dimensional, you can do completely parallelly without any interaction. But if you go slightly higher dimensional regimes, you would require some degree of adaptivity. And the natural question is it necessary? Well, the lower bound says that you cannot get accurate and general algorithms that use no adaptive interaction. So, adaptivity is some sense necessary. This is just to wake you up. This is a slide for linear regression, just to say what setup I'm working in. I'm working with ERM. Basically, a bunch of data samples. I have the empirical minimizer, and I want an algorithm which produces a model theta priv, where the empirical loss is close to the best possible empirical risk. Okay. So in this talk, I'll not focus on population risk. I'm just focusing on the empirical risk, just for simplicity of the talk. Okay. And this is just a picture of linear regression, where the loss is essentially least squared loss. So this is what we know in terms of upper bound. If you have one-dimensional or constant dimensional ERM problems, then you can get the optimal excess risk, which is 1 over square root of n times epsilon squared in the local privacy model with zero adaptive interaction. If you are doing linear regression, you get square root of p over n epsilon squared with zero adaptive interaction. In our paper, we also have the lower bound, which says that for linear regression, this is actually tight. So this was not known earlier. The lower bound is also new in the paper.
For any protocol, or just non-adaptive, or non-interactive? Or
No, so for any protocol, the linear regression, the ERM loss is this much, and this is tight, and in particular, we get this with no adaptive interactions.
For LDP protocol?
Huh?
For
For LDP protocol.
For all LDP protocols?
For LDP, all LDP protocols.
even multi-round when I ask the user multiple queries?
So you should look at the lower bound.
Okay, just exists there. Oh, this is
Yeah.
just some. This is just a sample.
This is just sample complexity. Okay. If you're dealing with general ERM problems with Lipschitz loss, which basically means that the gradient of the loss functions are bounded, then you would require square root of p over n epsilon squared. This is optimal error. In time, or in adaptive interaction, which is min of the dimensions times log of n and n epsilon squared upon the dimensions. Let me parse this statement in a bit. If you have strong convexity, you can get the optimal accuracy with a much lower number of adaptive interactions, which is not kind of surprising. So let me parse this kind of weird expression. If you have convex optimization problems, typically your accuracy is given, let's say if you want to reach an error of alpha in your optimization, then you would require roughly around p times log of 1 over alpha rounds of interaction, or 1 over alpha squared, whichever is smaller. This essentially is the same term. Given the accuracy you can reach is square root of p over n epsilon squared. Why am I saying this? This comes from purely optimization literature, and with differential privacy, what you can do is you can reach the same level of accuracy without hurting the rate at which you reach that level of accuracy. So in some sense, differential privacy does not affect the rate of convergence up to the error. So it will saturate there. Does it kind of make sense? Good. Okay. So these are the upper bounds, and we'll show that for these two classes of problem, you need some degree of interaction. In particular, the later work after ours, which actually showed that this is actually necessary. So the degree of interaction is actually tight. Okay. In terms of lower bound, so what we show is that to achieve an excess empirical risk of alpha, any gradient-based method that makes at most 2 raised to the power of small o of the number of dimension queries to the gradient oracle needs to make at least omega of log of 1 over alpha adaptive interactions with the data. Okay. So this was our lower bound. you can actually improve this. I'll show in a bit.
So can you remind me what P is again?
P is the number of dimensions.
P is the number of dimensions.
Parameters, like statistics.
Yeah. Just a quick question. We know that the gradient-based methods are much weaker than LTP. Then why is this a lower bound than LTP protocols?
Oh, so this is a lower bound for LTP protocols with gradient-based methods.
I see. So, but those are weaker than general.
Yeah. This is just for gradient-based methods, and in fact, this lower bound is independent of LTP protocols. This is just a lower bound for optimization problems.
So yes, the question: do you have a lower bound for LTP?
No. Generally. And when I say for linear regression, the accuracy lower bound, not the adaptivity lower bound.
Right.
So, how does this lower bound work? I will go into much more detail later on. But typically, the idea is that we'll construct pairs of function which will be different inside a small regime, and they'll be identical outside. So basically, if you start throwing darts at the board, you have a very low probability of hitting this ball. But once you get the information about what the value of the gradient or the function from this dart, then that will tell you where the ball is, and that round of interaction would allow you to go inside this ball. So this kind of will enforce at least one round of adaptivity. So we should go in much more detail into it. Okay. So this is the lower bound. So there are newer lower bounds, which basically says that log of 1 over alpha was not tight. You can actually extend it to min of 1 over alpha squared and p raised to the power 1/3. P is the number of dimensions. If you look at this term 1 over alpha squared, this is essentially what gradient descent allows you to get. So if you're not in, if your dimensionality is sufficiently high, then essentially gradient descent is the best what you can achieve. And the version of the result from BS18 essentially is an adaptive interpretation of the classic Nemirovsky-Yudin lower bound. So if you look at the original Nemirovsky-Yudin lower bound for gradient-based methods, essentially you can do some surgery on the lower the function which they construct to actually get an adaptive version of it. And essentially this paper does this modification to the Nemirovsky-Yudin lower bound to get 1 over alpha squared. So all this is saying is that gradients-based method is the best you can do.
Sorry, Mr. Which paper is BS17 or 18?
Oh, this is Yaron Singer and Balinsky.
Okay, I'll look at it.
So this is some description of the previous work. The Cleaners paper introduced the problem of local private learning. Ducci et al. Gave tight upper and lower bounds on accuracy, which resulted in an algorithm where the number of adaptive interactions were equal to the number of devices. And this was some of the work that was done on the applied front of things. And essentially, while doing this work, the whole problems, basically we landed up in this problem, and that kind of gave positive and negative results for us. So it's kind of interesting that pure engineering problem lands up in kind of research questions, and this I'm not making up. Okay. Hopefully I have given you some kind of motivation to stick around for the algorithm and the lower bounds. So let's go into the design of algorithms for this problem. Super simple problem. Let's do single parameter learning. P is 1. And here I will promise to you that we can do single parameter learning with no adaptivity. And we'll have some new ideas showing that, okay, this algorithm is kind of cute. So high level idea is we'll reduce the problem of ERN to finding median in a data set. I'll just wait for 5 seconds. If it seems obvious to you, great. If it doesn't, next few slides will tell you why it is kind of interesting.
Median or model?
Median. So you have a bunch of data samples. You are training ERM model with local differential privacy for one-dimensional problems, and we'll do some surgery and we'll translate into finding median of a bunch of data samples. So how do you do that? First observation is that if you have a convex function, the derivative of the function, I will talk about the derivative because I'm dealing with one-dimensional function. The derivative is a monotonic, it's a non-decreasing function, right? Which essentially means that I can represent the derivative as a convex combination of a bunch of step functions. Now you should start getting a sense of how this translates to a median. Now what I will do is, I will take my convex function, the loss function on the data sample, and do an approximation which will be essentially a convex combination of a bunch of absolute value functions. Because the derivative of an absolute value function is just a function. So what I'm doing is just a functional approximation. The important point is it is a convex combination. Now what I will do, for each of the data sample, I'll take my loss, write it in this convex combination of absolute value functions, and then what I will do is, I will just sample a function, one absolute value function with probability that is given by the value in the convex combination.
What are the CIs?
Huh? Oh, ZIs are, like I told you, right? I will approximate this loss function as a convex combination of a bunch of absolute value functions. So this is the center of this absolute value functions. Okay, let's go back in a bit. So I'm pretty sure I have enough time.
No, you have these, Z's, and V's.
Yeah. So you have the loss function. So the loss function can be written as a convex combination of absolute value functions, and each absolute value function is centered at z1 till zk. So what I'm doing is I'm putting a net on the range space from -1 to +1, and at each of the net point I'm putting an absolute value function.
So is Z just like the empirical risk minimum for a single device?
No, z is the minimizer for the absolute value function for this particular absolute. It is a point where the function is set.
Does it matter how big K is?
Huh?
Does it matter how big K is?
It does matter how big K is. You'll optimize that later. And
But presumably each person has a different function, right?
yes, and each person will do this approximation on her device. Okay. So now you get a bunch of absolute value functions. Once you sample with the convexity parameter, and essentially you get a bunch of absolute value functions.
So what are the V's?
Huh? What are the
V's.
What are the V's? Well, whatever the absolute value function is sampled.
The V is the sampled Z?
Yeah, sample Z.
Okay.
Yeah. For the definitive notation. V is basically the sample Z, and now it is about finding the median of a bunch of data points.
You want to talk, sorry.
Yeah. V is now this is about equivalent to finding the median of a bunch of data points. Yes.
So the alphas also depend on D, right?
Yeah, alphas also depend on
It's
D.
supposed to be alpha ij or alpha I1. Oh, it's alpha 1. Okay, so you're using subscripts, superscripts.
Yeah. So, yeah. So these all depend on data sample, and it is super important that this is done on the device. Yeah. Good. So the claim is that by doing this kind of surgery, you are not introducing additional error beyond what LDP would force you to introduce. Now the problem is much simpler. I forget my loss functions, I forget everything. each device has a data point, and I want to find out the median of those data points and the local differential privacy. Right? How do you do that? Well, this is how the picture looks like. Median is basically the minimizer of this loss function. So, first, put a alpha net on the space. Then, what you do, represent each of the absolute value function with their slopes. The slope only translates from 0 to -1 to +1 at some point, right? For each of the absolute value function. Good. So I'll just break it up into two parts, where one part goes from -1 to 0, another part goes from 0 to +1. So basically the slope changes from -1 to +1, so I'll go from -1 to 0 and 0 to +1. And let's now look at, and the most important point is, if the server from each of the devices knows this information, it can find out the median. Right? Because the derivatives of the function will give me where the median lies. So all that translates to is, now I have to give a differentially private way, or LDP way, of sending this particular information of the step function. Right? What I will do is, I will hammer it with the binary tree aggregation protocol by DNPR10 and Song, Chan, and Shi. Yeah, 2010. I forgot that. Yeah, essentially, what happens is, like, you see that this function changes from 0 to 1 in one place. So there's literally one bit of information here, and you essentially use the binary tree aggregation to kind of send out the prefix sums. Right? So how much error do you incur by doing this? Well, error is like log 1 over alpha by epsilon per node, and you would get to, since there are log of 1 over alpha nodes, your error would go to log of 3 over 2 1 over alpha. So now what you do is, the server essentially aggregates this differentially private versions of the step functions and uses that to find out the median. So notice that what I did, I could have approximated each of the loss function by a net. What I did is, I approximated the derivatives by the net. If you actually work out the math, just by putting a net on the function space, you would not get the optimal error. So to get to that 1 over root n error, you need to do this derivative space on the derivative. Okay. So if I look at the formal accuracy guarantee, under appropriate choice of the alpha net, you would get around 1 over square root of n epsilon error. And this is tight. Now, a natural question that arises is, like, if I can extend this kind of a technique to higher dimensions. Up to constant dimension, you may be a bit happy, but beyond that, no. The accuracy guarantee will go exponentially over to the number of dimensions, because a natural way to do it is, like, first choose a random direction and try to optimize in that direction, but your accuracy will obviously be worse as you go in the number of dimensions, because the volume becomes more and more. So this does not work. Although in higher dimensions you can get an optimal accuracy of square root of p over n epsilon squared using a combination of two methods. One is differentially private variant of the gradient descent method. We all know that, like, if you take the gradient, add noise, and do a bunch of iterations, then you would get a differentially private algorithm. The variant we actually analyze in this paper is what is called the cutting plane method. It's basically a binary search in the high dimensional space. The choice of the algorithm is not that important, but it has an important message behind it. we know that if you are training differentially private methods, the dependence on dimensionality is unavoidable. Right? If you are doing just pure convex optimization, if you are ready to pay a dependence in dimensionality, then you can get what they call linear convergence, meaning that you can, to go to an error of alpha, you require log of 1 over alpha rounds. But there is a dependence on the dimensionality, like dp times log 1 over alpha. If you want to get completely independent dimension independent result, you get to gradient descent is 1 over alpha squared. But the fact that differential privacy would force you to have a dependence on dimension, there are regimes where this kind of binary search or cutting plane methods are better than gradient descent methods if you're dealing with differential privacy, which also means that you have to do an analysis of cutting plane method, not super hard, but one has to do it. Okay, so that's about the algorithms.
10 minutes.
Okay, coming to the lower bounds. Okay. Since this talk was prepared in 2017, you will get a stale version of the lower bound, the newest and the best lower bound. You should look at the paper, but the ideas are somewhat similar. So what I'm trying to do is, I'm trying to show that you would require some degree of adaptivity to get to an error of alpha. Okay. And this lower bound is independent of differential privacy. These are purely optimization lower bound. So if you are not allowed to make exponential number of queries in the dimensions to the function or the function oracle, then you need to make at least log of 1 over alpha rounds of adaptive interactions with the data before you actually go to an error of alpha. Okay. So how does this work? I will construct a function which would behave as follows. So to go to reach an error of alpha in your optimization, you need to be in this small ball in the whole space, in this blue ball. Okay. Now, for the time being, just forget about the pink and the green ball. Okay. Now, if you're trying to optimize the function, what you can do is you can just throw darts on the space and evaluate the function, right? Okay. By throwing darts at the space, the probability of hitting this small ball is very little. Okay. Now, if I have two functions which are identical in the outer space and differ slightly within the ball, then just by throwing darts at the space, you will not be able to figure out which function you are dealing with. And then this you can do it recursively. Basically, you will construct the function in a sequence where once by throwing the darts, one thing I need to say, once you throw the darts at the space, unless you see the answers to those darts, you don't know where even this ball lies. But once you see the answer, you know where the ball lies, and you can go, the next query can be inside the ball, and that can help you tease apart the two functions. But what have I done in this process? I have enforced one round of adaptivity. You have to see the answer before you know where the ball is, where to make the next query. And this construction, you can do it recursively. But the problem with this type of construction is that if you do it recursively, your space reduces exponentially because the volume kind of the balls reduce exponentially, and hence you can do it up till log of 1 over alpha rounds. Now an interesting question is, what did I say? I will construct a pair of functions which are slightly different within a ball and identical outside. And these functions have to be convex, because I'm dealing with convex optimization, right? If you want as a homework exercise for your class, this is a good exercise to give. How to construct this pair of functions. The answer to it is like super simple, but it's kind of a trick. Okay. Just before I go into that construction of the function, so prior lower bounds, Nemirovsky-Udin was non-adaptive lower bound, but this recent paper BS18 essentially shows that you can translate that into an adaptive lower bound. Nesterov 2004 proved a lower bound for gradient descent type methods for the number of rounds of adaptivity, but he made a crucial assumption which said that the points over which you are making the gradient calls have to be in the span of the gradients which you have seen so far, which is typically true for gradient descent, not for private gradient descent, because you are dealing with a noisy process. So you will not lie in the span. So in particular, both of this lower bound acids do not apply to the adaptive case.
It's just one query per round, but it's a sequential lower bound.
It's a sequential lower bound. It's an
like adaptive lower bound.
Yes.
Just one query per round.
One query per round.
But
Good. Okay. So the challenge is that, to do this lower bound, the challenge is that you have to construct two functions f and g that are same outside a set C and differ significantly inside that set, and these are convex functions. Okay. Any thoughts?
what does significantly mean?
Like they should differ. The minima should differ.
Okay.
Yeah. It's a talk, so we'll continue. So I'll choose a function f0, which is basically the absolute value function and a cone in the high dimensions. And I'll choose another pair of functions f minus 1 and f plus 1, let's say. One is centered at c minus 1 and another is centered at c1, and their slopes are lower than the center function. We know that max of two convex function is always a convex function. So now once I do this, in this regime, the yellow function dominates over the blue function, but outside this regime, the blue function starts dominating. Right? So now my function construction would be basically, the first function would be max of f0 and f minus 1. So I have this pivot function and I construct f0 and f minus 1. That's the max of it is the purple function. The other function would be essentially max of f0 and f1. So this is the other function. So these two functions differ in this regime and they're identical outside this regime because that is dominated by f0. And these are convex functions. Well, you can use this essentially to, this pretty much gives you the lower bound. So I'm almost done with my talk. So in this talk, what I showed you is like new algorithms that use little or no adaptive interaction. Some lower bound which says that you cannot get accurate and general algorithms that use no adaptive interaction if you are using gradient-based methods. If you don't use that, maybe you can achieve it, maybe you cannot, but the lower bounds what we have is for gradient-based methods. And I have some comments about the open problems. So I told you that if you want to get the optimal algorithm for general ERM problems in the local model, with the best round of adaptivity, you will use either a mix of cutting plane or gradient descent method. Well, cutting plane is a meta algorithm. Essentially, it resolves to finding out the center of gravity of a weird convex body, which we do not know to find as is. So there are variants in the non-private world. The question is, do they extend into the private world? Something like Vaidya's algorithm and things like that. So that is one question. So can we actually have an implementable algorithm for cutting plane with differential privacy? So the adaptivity lower bounds what we have are not specific to local differential privacy. These are like generic lower bounds for convex optimization. The question is, are there adaptivity lower bounds which are specific to local differential privacy? And the last question is not necessarily about local differential privacy, but rather about general private ERM. Is it always true that differential privacy does not affect the rate of convergence for an ERM. So if you look at the proofs of private gradient descent methods, essentially what, if you kind of tease apart the terms, you will see that if you increase the number of rounds, the iterations, you do not hurt accuracy, you will just saturate. But the rate at which you go to the accuracy that is achievable under differential privacy is the rate at which you would have gone to that accuracy even without privacy. So go at like 1 over square root of t. The question is it always true? And that's where I would end my talk. Questions? Yeah.
Nice job.
I'll ask you a question. So your lower bounds as well as the subsequent lower bounds assume that the gradient oracle is giving you exact gradients, right?
The gradient oracle is giving you exact gradients. Yeah.
Are there any potential stronger lower bounds that you can get from a gradient oracle that's giving you noisy gradients in some noise model?
Potentially, and that's where this kind of the open question is like, under LDP can you get stronger lower bounds?
Okay, if there are no more questions, let's thank the speaker again.